Hello everyone. In this video we are going to talk about Z-transform and of course the inverse of Z-transform. The material again is coming from Discrete Time Control Systems by Katsuhiko Ogata. So Z-transform for digital systems is the equivalent of the Laplace transform that we learned for classic control for continuous systems. Laplace transform, if you remember, converted the differential equation to an algebraic equation which can easily be solved, and then applies an inverse to bring it back into the time domain, right? So you go from T domain to S domain and then back. Z-transform does a similar thing but on a difference equation, because in the discrete domain your differential equations are now converted to difference equations, and if you want to solve them, first you convert them to an algebraic equation through what transform? Through the Z-transform. So you take them from the T space again, or sample space, to this Z space. You solve the algebraic equation and then apply inverse and bring it back to the time domain. Okay, so it's very similar to Laplace transform. Of course, the Laplace transform and the Z transform, they are not identical when you look at them. One is an integral, one is a series, and the terms in them are different, but we can see that they are easily related to each other. I'm going to do that in the next video, and this video is to see the definition of that, apply to some examples, look at the tables of it, and then talk about the inverse of it. So if you have a time sequence of data, x at 0, x at t, x at 2t, right, a bunch of samples from an actual signal x of t, which is sampled at t equal basically k times t, where k here goes like 0, 1, 2 all the way. Then if you want to apply your Z-transform on this sample, the way to do it is this. It's a summation, goes from k of 0 to k of infinity of x of kt, that x at that time point, times z to the negative kt. Remember, Laplace transform was what? It was f of t, or x of t, let's say. It was x of t times what? Times e to the negative st dt. And it was this integral, right, from 0 to infinity. So here, first of all, integral is converted to sigma because you have a finite number of points, or if they are not even finite necessarily, that they are not at a continuous range of t, they are at a specific time point. So you, instead of integral, use a summation, right? And then instead of this exponential term, use this power term, z to the negative k. So if you want to expand it, that's going to be like x of 0 plus x at 1, or 1t in general, times z to the negative 1 plus x at 2t times z to the negative 2 all the way. Okay, so this is how you convert a signal in the time domain to a signal in the z domain. Okay, now for most of the series, for most of the signals, this formula in 1 will converge to a closed form solution for when the magnitude of z is bigger than some number r, where the number r, that radius, is called the radius of absolute convergence. I'm going to show you in an example. But we want to know that this summation, this series, will converge only for some specific values of z, not for any value of z. Okay? Let's go ahead and look at an example here. So the simplest probably example you can consider is a unit step function, which is 1 for t's bigger than or equal 0, and for negative t's it's 0, right? You all know the unit step function like that. So what is the Z-transform of that? You know, if we call this guy like us of t, then the Laplace of that would be what? Would be 1 over s, huh? So what is the Z-transform of that? So x of z is equal to summation k goes from 0 to infinity of x of kt, z to the negative k. Now x at any kt where k is bigger than or equal 0, this entire thing is just going to be 1 times z to the negative k. So this is simply what? Summation of z to the negative k, k from 0 to infinity. So it's like basically 1 plus 1 over z plus 1 over z squared all the way. And clearly, as you know, this is a geometric progression where the terms are all multiplied by 1 over z. So this is going to converge to what? If you remember a geometric progression like a times q squared all the way, right? The summation of all of that will converge to a over 1 minus q, the first term divided by 1 minus the q term. So that's exactly what we have here. The first term is 1 minus this z inverse, which is the difference between each term and the next. And if you simplify this, it's going to be z over z minus 1. Now, under what condition this will converge? If you remember from geometric progression, this is converge if the magnitude of this q is less than 1. Now, in this case, this q is 1 over z, so magnitude of 1 over z is less than 1. That means magnitude of z has to be bigger than 1. Okay, so the z transform of its step function is what? It's z over z minus 1 if and only if what? If this magnitude of z is bigger than 1. So you clearly see this is a circle around origin. If you look in the complex region, right, with the radius of 1. So here are the radius of absolute convergence is 1. And anywhere outside this, you have what? You have the z transform. Okay, so if this is the imaginary axis and this is the real axis. Okay, so that's the z transform of it, and this is that radius of absolute convergence. Now let's look at a couple of more examples before we look at the table for the z transform. So what about the ramp function, where it's bigger than 0 or equal 0, it's t, other than that, it's 0. So here, x of kt is going to be equal to the kt. But t is not dependent on the sigma, which is over k, so I can bring that t out, right? This thing is just kt. And as I said, t does not depend on k, so I can bring it out. And then what? Then the summation is going to be summation of k, z to the negative k. So it is basically terms like if k is 0, it's 0. But then the next term is when it's 1, it's 1 over z. Then you get 2 over z squared. Then you get 3 over z cubed, and so on and so forth, right? And if you know series, you know that the summation is going to be what? It is basically the summation of all of that. When you add all these terms together, that is an expansion of what? That is an expansion of z over z minus 1 squared. If you do an expansion of this, okay, if you do a Taylor series or Maclaurin series for this guy, then your this function will be equal to that series. So, and you also have that t, so it is going to converge to that. Yeah. So, what else? If you have a polynomial function. Now, polynomial function, when we talk about polynomial function in discrete space, we are not talking about terms like t squared or t cubed. So it's not going to be like kt squared or kt cubed or kt to the n in general. It's actually the other way around. If you look at it, the definition is a to the k. So a is the constant, k is the variable. So the term that we are talking about is something like this, a to the t. And this t is going to be replaced by kt, or k in general. So actually this polynomial that we are talking about here is kind of like a power function that we had in the time domain. So it's a to the k, where a is constant for k's that are 1, 2, 3, and it can also even be 0. And then anytime other than that for negative k's is clearly what? It is clearly 0. Okay? So what's the answer? So in this case, x of k or kt. Now you might say, where is t gone? In general, in discrete time, many times you see that x of kt is replaced by x of k. If you see that, do not be surprised. They do not put that t always, okay? It has this t implicitly in it, so when we say k, means the kth sample. What time is it? K times t, of course. But if you see, instead of x of kt, there is only x of k, it doesn't mean they forgot the t. That means t is implicated. So this x of k is a to the k, then times z to the negative k. And if you expand this, this is clearly what? So the first term is like 1. The next term is a over z. The next term is a over z squared, and all the way. Again, this is a geometric progression where the summation is the first term 1 over 1 minus the a over z term, which you can see here. And if you simplify that, it's going to be z over z minus a. It is converging, of course, when the magnitude of this is less than 1. That means magnitude of z has to be bigger than a, or bigger than magnitude of a. Okay, so that is the radius for this one as well. You can find the radius for each and any one of them. So one of the things is for z transform, one of the formulas that you have to be good at is that geometric progression thing. That formula of a over 1 minus q, this formula for magnitude q less than 1, this is an important formula if you want to be good at calculating z transforms. You need to know that formula. Okay. And a couple of other well-known functions. One is an exponential function, e to the negative at. Again, x of z is going to be e to the negative akt here. So for this t here, we replace it with kt, and z to the negative k. And again, if you look at these, it is similar. The first term is 1. The next term, if you look, basically, they both share what? This whole thing can be written as z times e to the at, the whole thing to the power negative k. So this is that q term. So the summation will converge to what? 1 over 1 minus that guy, which is that. Okay, because this is like negative 1 to the k, right? So it's going to be this term to that negative 1, which you can see here. And if you simplify it, this is your result. Again, here, the magnitude of this term, which is this guy here, that magnitude of that has to be less than 1, which means the magnitude of z has to be bigger than 1 over e to the at. Okay, so that is your r. And finally, a sine function. Now for sine function, we replace it from complex numbers with sine of omega t. We replace it with 1 over 2j e to the j omega, right? Do you remember that? So we replace it with this, e to the j omega t minus e to the negative j omega t. Okay, this is that sine of omega t. And for t, we replace it with capital T times k. And now each one of these terms, when multiplied by z to the negative k, they are the same as the previous one. Because the previous one is an exponential, and each one of them is now an exponential, except the exponential has an extra j in it. Okay, so you do it for each one of them, and you simplify, and the j will go away. You get this. Get z sine omega t over z squared minus 2z cosine omega t plus 1. Okay, so that is what the z transform for the sine function. And you can do a similar thing for cosine. If you want to have a cosine of omega t, then cosine omega t is what? Is going to be just 1 over 2 times e to the j omega t plus e to the negative j omega t. Okay, so if you do that and write it that way and use the top formula, you can get the cosine. Now what is it? That's this guy here. So this is cosine omega t, this is sine omega t, and this table that I'm about to show you has a term for most of the functions that you typically use in engineering. So the next thing we're going to look at is the z table, where on the left side you have the time function or the series, and on the right side you have what? You have the equivalent z. The first function that you have is the famous Kronecker delta function, where it is only 1 for k of 0 and 0 elsewhere, right? So it's a simple spike. That's all it is. If you plot it versus t, and you call this delta of t, basically you only have a 1 here, and everywhere else it is just 0. Okay, and you can easily show that the z transform of that is just 1. Why? Because the only term that would remain when you write this series is just for k of 0. For k of 0, this is 1. For other k's, this is 0. So all other powers of z going to go away. The only term that is remaining is x at k of 0, which is 1, times z to the power 0, which is also 1. So the whole thing is going to be a 1. If there is a delay, then it's going to be z to the minus k. In general, any signal that is delayed, let's see if I have it somewhere here. If I don't, that's fine. Any function that is delayed, its Laplace should be, sorry, I keep saying Laplace. Its z transform should be multiplied by z to the negative k. For instance, remember that the step function us of t, what was the Laplace of it? You just have it up here. It's z over z minus 1, right? Now, if I have the us t minus 2, what is it? That is going to be this z over z minus 1 multiplied by what? Z to the negative k, where k is the time of delay, so it's 2, so it's going to be like this. So if you simplify it, this z over 2 comes to the denominator, so you get a z over z times z minus 1. Okay? Yeah? So this is what? This is a delay. In general, z of x of t minus k is going to be x of z times what? Z to the negative k. This is called the shift on the time axis, which corresponds to a z to the negative k. Remember, in Laplace transform, it was a negative exponential. It was negative e to the s k. Here it's z to the negative k times that z transform of the function. And then here is, of course, the step function. Then we have the exponential. Then here is the polynomial, that t. If you want t, then it is going to be this. If you want t squared, t cubed, right? You have them all as well. Then you have t times e to the negative at you have. You have t squared times that. You have sine and cosine omega. You have the damped sine and cosine if you want. You have the polynomial, this polynomial, which is right, the power function. 1 minus a times z inverse. So the only difference between the step function and this polynomial is what? If you look at these two, look at them, compare them, the only difference is there is extra a that is pre-multiplied by z inverse. And you're going to see this guy a lot. So this one is one of the important ones. Okay, and then you can multiply k by a to the k and get that, and so on, and even something like this. Okay, so this is what? This is a table of z transforms, and it is very useful. Now in MATLAB, if you want to do it, there is this command called ztrans, but you have to define it symbolic. This is a symbolic command. So if you define symbolic k and t and say, for instance, f equals sine of kt, and then say capital F is z trans of f, that should exactly give you what? Exactly give you this guy here. Okay, let's practice that. So here we go to MATLAB and say sims k and t. And then We say that f equals sine of k times t, right? So let's do it. And finally say f equals z trans of f. So this is a symbolic tool. And there we go. Z times sine of t over z squared minus 2t cosine z plus 1, which is the same as this, or if you simplify it, that's basically this guy that I derived for you earlier. Okay, so this is a powerful command and you can use MATLAB. Now, a couple of other things. Z transform has a bunch of properties, just like Laplace transform, that I want you to see. One of the most important ones is a linear operator, just like Laplace transform. Z transform is also a linear operator. So if you apply Laplace transform on A times X, it's going to be A times Z transform of X. If you apply it on AX1 plus BX2, it's going to be A times Z of X1 plus B times Z of X2. Okay, yes. Then here, if you look, if you apply it on x of k plus 1, so the function is basically 1 second ahead, then the z of that is going to be z times x of z minus z times x of 0. If you do it on the one that is 2 sample times ahead, then it's going to be z squared x of z minus z squared x of 0 minus z times x of 1. And in general, you can have it to be k sample times ahead or k sample times behind. This is the behind one that I showed you, remember? It's going to be z to the negative k times that, and if it's k steps ahead, not only you have z to the kxz, you also need to include all of these initial conditions, x of 0, x of 1, all the way to x of kt minus t. Okay, yes, so that is important. Then if you multiply t by a signal, in the z domain, you have to take a z derivative and multiply it by negative tz. Yes? If you multiply an exponential by the signal, then in the z domain, you multiply that z, the inner argument of function, by e to the a. Okay, so this is the scaling in the z domain. On the other hand, if you multiply it by a to the k, the signal, by the polynomial, then you have to divide z by a. That's also dividing division in the z domain, right? And so on and so forth. So for instance, before I go to the rest of it, let's just look at one example here. For instance, let's say, what is the z transform for, let's say, t times sine of t, right? So what is it? Sine of t, we have it up here, remember? Or if you want, we can go and pick this. But since it's t, so this is just going to be 1. Yes? So it's going to be z sine t over z squared. Right? Let's write it. Z sine t over z squared minus 2z cosine of t plus 1, if I'm not mistaken, yes. So this is the z transform of sine. Now that is pre-multiplied by t, what should I do? Look, what I need to do is to take a derivative of that with respect to z and pre-multiply it by negative z, by negative tz. So it's going to be negative tz times what? Times the z derivative of this function. And this is a ratio, so it's going to be derivative of numerator times denominator. So it's going to be sine of t times the whole denominator minus derivative of denominator times z sine of t. and then the whole thing divided by the denominator squared. Like that. Okay, let's go back and let's look at some other properties. So one of them is the initial value theorem here. And the other one is the final value theorem. So it says x, the signal at time 0, is the limit of x of z as z goes to infinity. And x at infinity, the steady state value of the signal, is equal to limit as z goes to 1 of 1 minus z inverse times x of z, if this limit does exist. So let's take a look at one. For instance, let's look at sine of t. Remember, sine of t was what? Again, it was this function. So what's the value of this signal at t of 0? We know sine of t at t of 0 should be 0. So based on this formula, it should be the limit of x of z as z goes to infinity. So if I take this limit of this as z goes to infinity, since the order of denominator is more than numerator, that is equal to 0. And of course, that is equal to sine of t at t equals 0. So you see, it is absolutely working. Or if I want to look at the exponential one, remember that the exponential one, if you look at it, let's get the exponential. This is the exponential z over z minus e to the negative a times t. That is for e to the negative at. So if I want to know what's the value of this as t goes to infinity, clearly we know it's 0. We said it should multiply this function by what? By basically 1 minus z inverse, and let z go to 1. If we look, when z goes to 1, what's going to happen? This term is going to be 0, this term is going to be 1, this term is going to be 1. This is not going to be equal to 0 in general. This whole thing is 0, so it's just going to be 0. And of course, that's the same as limit of this negative exponential as t goes to infinity. So you see, that's what? That is the initial and final value theorem. And there are other things too. For instance, if you have the backward difference of a signal, the backward difference of a signal is 1 minus z inverse x of z, the z transform of that, and the forward difference of a signal is z minus 1 times x of z minus z times x at 0. And these two clearly are coming from these previous properties, these guys. They're coming from this and this. And because it's a linear operator. And then, for instance, if you apply z transform on a summation of a series, then it's going to be 1 over 1 minus z inverse times the z transform of the series itself. If you take partial derivative with respect to parameter a, not time, that's the same as taking partial derivative with respect to a of the z function. So a, which has nothing to do with time in the z domain, also will have nothing to do with z. If you multiply x by k to the m, then in the z domain you have to pre-multiply it by negative z and then d over dz to the power m. Okay, so for instance, if m is 2, then this is going to be z, negative z dz to the power 2. Okay, so you have to take that and use power 2. And here is the convolution of two signals. If you have convolution of two signals in the z domain, it's going to be multiplication, just like Laplace transform. And of course, it says that the value of summation of a signal k goes from 0 to infinity is the same as x, but for z of it, you plug in z equal 1. So the x of z at z equal 1 is the summation of all terms in the series of something. For instance, if we apply it to, let's say, the exponential term, right? So this x of k is basically that e to the negative kt, or negative k in general. Then if you find x of z for that, so here you want to do the summation of that as k goes from 0 to infinity. Then, let me write it here. We find the z transform for that e, which we already have it up here, remember? That's this guy, so 1 over 1 minus right? And then that e to the negative at times z. Let me make sure that I did it correctly. Believe it or not always, or let's do this one. This is easier. Z over z minus e to the negative et. That is easier. So it says plug in 1. And if we plug in 1, that's exactly the summation of this. Because if you write it, this is like 1 plus e to the negative 1 plus e to the negative 2, or 2t in general, right? And so on. And as you know, this is, again, this formula of a over 1 minus q, which is, in general, in this case, a is 1. So you're going to get that. Okay, so these are some important properties of the z transform, as well as what the z table. So now that we know about the z transform and the z table, let's go ahead and talk about the application of this z transform. Remember, we said the application is to convert a difference equation into an algebraic equation and solve for the z transform of the solution, so later we can apply an inverse on it. Okay, so let's go ahead and talk about this part. Okay, so if we have this difference equation of x of k plus 2 plus 3x of k plus 1 plus 2x of k equals 0, and the two initial conditions are x of 0 equals 0 and x of 1 equal 1. If you wonder why we need two of them, because here it's basically, this is k plus 2, so this 2 here is similar to the order of a differential equation. So basically this term is corresponding to something like x double dot. This term is something like 3x dot, then plus 2x equals 0. Okay, so it's like a second order differential equation, but here is a second order difference equation, so it needs two initial conditions, because other than that there will be no way that you can calculate. When you plug in k of 0, for x of 2 you need x of 1 and x of 0, and if you don't have x of 0 and x of 1, you might not be able to calculate x of 2. Okay, yeah, so we need those. And here the question is, what is in general x of k? What is the solution x of k that comes out of this difference equation subjected to those two initial conditions? So in order to solve that, we apply a z transform to both sides of this difference equation, and of course z transform of 0 is 0. But z transform of x of k plus 2, if we go back and look at the properties, look here, x of k plus 2 is z squared x of z minus z squared x at 0 minus z times x of 1. So that's what you have right over here, okay? And Then z of x of k plus 1 is just x times, actually this is, should be z times x of z, not x. Z times x of z, sorry for the typos, minus z times x at 0. And so if you plug in the initial condition, knowing that x of 0 is 0, so that term goes away, x of 1 is 1, so that term will be a z. And here, this term again goes to 0. So you will get what? You will get z squared x of z, right? And minus z, so that is the first term. Then plus 3 times what? Here, z times x of z. And then plus 2 times z of x. And here, seems like I'm going back and forth between x of z and z of x, and that is not right. So let me fix it. Okay, this is how you should say it. Equals 0, and then here, the only term that does not depend on x of z, which is this guy, is going to go to the other side, and the coefficient of x of z is going to be z squared plus, basically, here it needs a z, plus 3z plus 2. So if you divide that z by the coefficient of x of z, this is your x of z. Okay, so this is the z transform of the solution. So now here I brought it from the time domain to the z domain, and I found the z transform of the solution. If I can apply a z inverse on this x of z, I should get x of k. So how do I apply z inverse? That's our next topic, and I'm going to show you. But if I know how to apply it, then I should get my solution. Okay? So this is about application, solving a difference equation using the z transform. But as I said, the last step of it always involves finding the z transform of an x of z. So how do we do it? Well, there are 4 different ways that you can do it. The first one is called direct division method, which is not going to give you a closed form solution, but it can just give you as many terms as you want if you keep doing successive divisions. How would you do that? Well, what you need to do is to write that x of z into an infinite power series in terms of z minus 1. So if you write this as summation of k goes from 0 to infinity of something times z to the negative 1, maybe to the power k, in terms of increasing powers of z minus 1, then of course based on the definition of z transform, this thing, whatever it is, it has to be x of kt. And that is exactly what you want. Right? So if you can write that in this manner, then you can find this, but the problem is not always an easy thing. So let me show you. First thing is you have to write this in terms of z inverse. Remember, the goal is to write it in terms of z inverse. How would you do that? You divide both numerator and denominator by z squared, by the highest power that you have. So that becomes z inverse. This z inverse over z squared becomes 1. That becomes 3z inverse, and that becomes 2z inverse squared, or z to the negative 2. Now what? Now you divide the numerator by denominator by successive divisions. So you say, hey, look, z inverse divided by this denominator, what is it? If I want to divide that z inverse by that 1 plus 3z inverse, and then plus 2z to the negative 2. If I want to divide, what would you do? You divide this by the highest order term, which is in this case 1. So you're going to get a z negative 1, and then multiply z negative 1 by everything. If you do that, you're going to get z negative 1 plus 3z negative 2 plus 2z negative 3. And you subtract. So these two terms would cancel. You get a negative 3z negative 2, negative 2z negative 3. And again, you divide it again by this denominator. So you divide the remainder. So now the term you will get is this guy divided by that. So you have to get now basically a negative 3z squared, which you can see over here, and you get some remainder. Again, you divide that remainder by this denominator and you get another quotient term and another remainder. So if you combine and add these quotients together, you can write your numerator as denominator times the quotient of the division plus the remainder terms. And clearly, if you here for the moment just neglect these remaining terms, the result of this division is just going to be this quotient term. And clearly this quotient term is written in terms of powers of z negative 1. So remember, the term that is multiplied by z negative 1, what is it? That's x of 1. The term that is multiplied by z negative 2, that is x of 2. The term that is multiplied by z negative 3, that's x of 3. So clearly here, x of 1 is 1, x of 2 is negative 3, and x of 3 is negative or positive 7. Okay, so you can find a few terms of this series. Do you have the general solution for it? X of k? Absolutely not. And you don't even know here x of 0 because it has not shown up. But x of 0 is going to be multiplied by what? You remember x of 0, here you don't have it, but x of 0 is going to be multiplied by a 1 instead of a z minus 1, z minus 2. Since you don't have any constant term here in this quotient, that means x of 0 should have been 0. So in this case, if you want to add one thing, you can say that x of 0 was also what? Was also 0. Okay? So here you could get 4 terms. Now, of course, that comes at the extra cost of doing 3 divisions. So I had to do 3 divisions here to only get 3 or 4 terms. If I want more terms, I have to do more. I have to keep dividing. And I can never get a closed form solution. I can only get a few terms. So if your goal is just to find the first few terms, this might be a good idea, but in general, that's not the best way to do it. Okay, so the next method, which is also not most of the time going to give you a closed form solution, is called the computational method or methods. So what is it? Here we either use MATLAB or we can do it manually by hand to calculate the response of the system to the Kronecker delta function. Remember that delta of t, that was a 1 at 0 and everywhere else a 0. That function, if you pass it as the input to the system, the output of the system is clearly the x of kt, okay? Yes, because just like Laplace transform, this is what we call the impulse response of the system. Okay, so let me show you both ways. In the first one, this is what you do. You define the numerator coefficients for this. It's a ratio. So the polynomial in numerator is 0 z squared plus 1z plus 0 constant. And the denominator coefficient is 1z squared plus 3z plus 2. Then you form your Kronecker delta function by having a 1 at 0 and a bunch of zeros to follow. So here, this is how I define this Kronecker delta function. I say at 0, the first element is a 1. Everywhere else, it's a 0. And you can make it as long as you want. The number of elements, the number of zeros that you use here determines the length of the response. So here I'm using 11 elements, so I'm going to get 11 entries of x of z. Then here I define my y as the filter of nom-denomin x. What is the filter? Filter means pass this x as the input to a system and get y. And what is this filter's basically transfer function? That is this x of z, or in this case, z over z squared plus 3z plus 2. Now, if this x is what? Is the delta function, then the y should be the same as what? Should be the same as basically the z inverse of that. Okay? Yes? So here I get the filter response of a system that is defined by numerator and denominator, and the input of it is x. And you see MATLAB gives you this as the response. So these are basically, in your case, these are the Laplace inverse of this z function. As you can see, the first term is 0, the next term is 1, then negative 3 and 7, and these are exactly what we found earlier. But here I can have more of them. This is x of 4, x of 5, 6, 7, 8, 9, and 10. You see, I have 11 entries because here I define this as x with 11 entries. If I want 50 of them, I can define it as 1 and zeros of 1 and 50, or 49. So I can use MATLAB to compute it for me and give me what? As many entries as I want. Again, no closed form solution. I cannot come up with a formula for these, what kind of formula they are following, but I can get as many as I want. And it's not as painful as doing all these divisions, successive divisions. So this is using MATLAB. Another way is to convert it into a difference equation, and using that find all of these entries. That is exactly similar approach. So you write this as the transfer function of a system, y over x, you cross multiply, so you get z squared plus 3z plus 2 times yz equals z times xz. And if you convert it back using what we know for inverse z, if you apply z inverse to this from the tables, you know that z inverse of z squared x y of z is y of k plus 2. 3 times z times y of z is corresponding to y k plus 1, assuming here 0 initial conditions. And 2 times y becomes 2y of k, and zx of z becomes x of k plus 1. So this is the original what? Difference equation that you can have for this system. And here, the x that you're going to use, again, is going to be delta function. So the value of it at 0 is 1, but anywhere else it is 0. So these are the values for the input of the system x, and now the goal is to find these y's. How? First, you plug in k of negative 2, you get y of 0 plus 3y negative 1 plus 2y negative, this is negative 2, equals x of negative 1. Now remember, all of x entries except for x of 0, they're all 0. So this guy is going to be 0. And since your y has not any value for negative indices, these are also 0. That gives you y of 0 equals 0. Then you plug in k of negative 1 in it, you get y of 1 plus 3y0 plus 2y negative 1 equals x of 0. X of 0 in this case is 1. This guy is 0. This y of 0 is already determined, that's 0. So you simply get y of 1 equal 1. Plug in k of 0 now, you get y of 2 plus 3y of 1 plus 2y0 equals x of 1. This guy is 0. Y of 0 is 0. Y of 1 is 1. So you get y2 plus 3 equals 0. So y2 becomes negative 3. And you see, your numbers are 0, 1, and negative 3, which are these three numbers. And if you want, for instance, now you can plug in k of 1. You get what? You get y of 3 plus 3y of 2 plus 2y of 1 equals x of 2. X of 2 is 0. y of 1 is 1, y of 2 is negative 3. So you get y3 minus 9 plus 2, which is minus 7, equals 0. So y of 3 should be equal to positive 7. And that is this guy. So you can keep plugging a new case, solving for this highest order term, and you can get these numbers one by one. Again, it takes a lot of computation because now you're doing it by hand, or if you want, you can automate it through MATLAB. And it is basically, that's the same as what this filter command is doing. That's exactly what this filter command is doing. Okay, so that's the same thing. This is called computational method. It does not give you a closed form solution, but you can repeat it in a loop and or with the filter command and get as many terms as you want. So now you might say, well, I really need a closed form solution. These are good, but I want a closed form solution. That's where you use the partial fraction expansion method. So here we use partial fraction expansion on x of z and convert it into lower order terms, linear terms in this case. If you have a distinct roots for the denominator or distinct poles, you might call it. And here, so this denominator has roots of 1 and 2, so we did partial fraction expansion on it. You know how to do it. If you don't, please look at the command in MATLAB, which I have in one of my lectures. If you look, one of my lectures is on partial fraction expansion. So look at that and you'll find all about it. And here, we want to write these terms the way that they appear on that table. So we divide everything by a z, by the highest order z, we get this and we get that. And if you look at this one, where did I see this 1 over 1 plus z inverse? If I go back and look at my table now, I probably can find one of these terms to correspond to that. Where is it? Most probably is a polynomial term. If you look at your polynomial, look here, look at this. Your polynomial is 1 over 1 minus az inverse. So let's go ahead. What was it? It was 1 over 1 minus az inverse. This is the Laplace of what? A to the k. If you look at both of these terms here, they are the same as this one. They are the exact same shape. Look at this. That's similar to that when what? When this negative a equals positive 1. So a in this case is negative 1. So this corresponds to negative 1 to the k. And this one, again, is very similar when this negative a equals positive 2. So a is negative 2. So it's going to be minus negative 2 to the k. So your solution is what? Negative 1 minus k minus negative 2 to the k. That is your inverse solution, and that is closed form. And if you plug in k of 0 here, you see you get a 0. If you plug in k of 1, you get negative 1 minus minus 2, which is positive 1. Plug in 2, you get minus 1 minus 4, you get negative 3. And you keep getting what? Each and every one of these terms. So they're all following what? Negative 1 to the k minus negative 2 to the k. And this is the closed form solution. So the best way to do z inverse is to do partial fraction expansion, make it into simplest term possible, and then look into the table to see which terms match it. That's the best way. Now, if you want to know what is the real definition of z inverse, does z inverse has a mathematical definition? Yes, it does. It's a complex integral, the same way that inverse Laplace is a complex integral. So how would you do it? The definition of z inverse of x of z, which is x of kt or x of k, is 1 over 2 pi j integral over a circle, over a loop of x of z times z to the k minus 1 dz. This is what? This is the definition of z inverse for x of z. What is c in this integral? It's a circle centered at origin such that all the poles of this inner term, this integrand, are inside it. If all the poles of this integrand are inside that circle, then any circle can be used for this complex integral. Now question, if you forgot, how would you do a complex integral? If you watch my video that I have on playlist Engineering Mathematics, I have 2 videos on complex numbers. In the second one, I talked about solving complex integrals. And the answer is using the things called residues. So what you need is to find residues of this integrand at the poles of it. So if this guy has a bunch of poles, m of them, and each pole is called zi, if you find the residue of this function at each and every one of those poles and add them together, that is the solution. And you might say, how do I find residue? The answer is the residue of this function at z equals zi, which if you call it ki, this is equal to what? The limit of z minus zi times the function as z goes to what? Goes to that zi. So you need to do it for each and every one of the poles, find these k's, add them together, and that should give you the solution. Really? Yes. Let's apply it to the same example that we had so far. Z over z squared plus 3z plus 2, that's x of z. Remember, the function we need to focus on is x of z times z to the k minus 1. So we multiply by z to the k minus 1, you get this. Now here, what are the poles of the system? Clearly, they are -1 and -2. So now k1 is going to be the limit of what? The limit of z minus zi, in this case z minus minus 1, so it's going to be z plus 1, times this function, which is here, as z goes to that -1. If you simplify here, you get z plus 2, z to the k, z goes to -1, you get -1 to the k, and here -1 plus 2 becomes 1. And k2 is the similar thing, but z plus 2 is multiplied by the whole thing, limit goes to z minus 2, so that will be simplified. Here you get a z plus 1, as z goes to -1, it's going to be -2 to the k, and then -2 plus 1 becomes a -1. So if you add these two terms together, that's your x of k, which is what we just found using partial fraction expansion. You see, so we can do the complex integral as well. So these are all of what different ways to do z inverse. And if you want to do it in MATLAB symbolic, remember we had the z-trans command for z-transform. We also have this command iz-trans, which is the inverse z-transform. And you can do that again on a symbolic function in terms of z. Okay, you can do that. Remember, we have Laplace and I-Laplace. We also have z-trans and I-z-trans. Let me show you that one as well. So here we say sims z, and then capital F, let's not call it capital F, it's capital X equals what? Z over z squared plus 3 times z plus 2. And then I z trans of capital X, look, -1 to the n minus -2 to the n, and here n is the same as k for us. Done. You see? So there are different ways you can do Laplace transform and, of course, what? Inverse Laplace transform. So hopefully this video was useful to you. You saw how to apply z-transform and inverse, how to apply it to solve a difference equation, and learn about the pairs of Laplace transform and the properties of Laplace transform. We're going to use it in future upcoming videos for analysis of systems in the discrete space and to design controllers and so on. Thanks for your attention. I'll see you in the next video.